Today we will move into chapter 2, which is controller design. PID controller design. This chapter discusses design to improve the system performance. Okay, we want to improve the system performance by looking into these two parameters, these two performances. First, transient response. We did in the subject 3133. We discussed transient response. We calculated overshoot, settling time, rush time, maybe I forgot to write peak time. All this can be improved by adding a controller. And the other one, we normally want to have zero steady state error. Steady state error. These are two important specifications in control system design. When we do analysis, we can calculate overshoot, all those transient response parameters. Then we can calculate error. Then we decide whether we need to use a controller or not. If the one that we obtain is not according to our desired specification, then we need to add controllers. This is an example. The block diagram here is an example of adding a controller. Okay, plant. This is the system, original system. Then we add a controller. Normally we denote by GC. C refer to controller, transfer function of a controller. When we draw root locus, usually we put here as K. K is one of the controller, which is known as a simple gain adjustment. Okay, K. K is, we adjust K so that we obtain what we want. And in order to design in this course, we will utilize root locus. That's why root locus is taught in chapter 1, then proceed with controller design by using root locus. But for your information, there are many other techniques which can be used to design a controller. We will proceed with designing PI. PI is proportional integral, and then PD, proportional derivative, and finally PID, proportional integral derivative controller. These are common conventional controllers or classical controllers. Okay. We will usually use PID to show how controller works. And in this subject, we will also show you how to do tuning. There are many techniques to tune. Tuning here refer to PID, because PID later have 3 parameters to be calculated or to be tuned in order to achieve desired response. Okay, let's start with design with gain adjustment, a simple gain adjustment. The objective here, as I mentioned just now, this is the one similar to the root locus that we designed. the objective is to find K. Okay, to find the value of K to meet desired specification. These are procedures in designing the gain adjustment control. First, we have to sketch the root locus. And then we assume the system is a second order system. Although the system is not second order, most probably many times third order, fourth order, or higher order. Initially, we will assume it's a second order system. Okay, without zero, and find the gain to meet the specification. We will do one or two examples. We have done this actually during root locus in rule 9. It's the same. It's also gain adjustment control. And finally, we have to justify the second order approximation. Okay, remember, we did yesterday example of partial test and final exam. There are many questions asking about second order approximation. And yesterday I mentioned we will discuss in detail in chapter 2. This is where we will discuss second order approximation. Okay, why these are important. Okay, let's see one example. A root locus is given. This is the root locus. The system is here, the transfer function. Design K so that the system operates at a damping ratio 0.5. This is exactly similar to the question in root locus. And this is gain adjustment control. When people say gain adjustment, this is the one. This is a kind of this. Okay, design K to achieve damping ratio 0.5. Let do. When I will go fast, we have done this. When you plot, you will get this. This is the pole at 0, -1, -4. Okay, 0, -1, -4, and these are the arrow of the root locus, going up, going down, and going up. Okay, when we want zeta 0.5, we do zeta line 0.5. We get this. This is the closed loop pole. Closed loop pole. This is the closed loop pole. Okay, to get damping ratio 0.5. I used MATLAB, but I couldn't get the exact 0.5. This is 0.45498. I need to properly get the point. Okay, yeah, and this about the same. And this is gain, K, because we want to find K. Okay, find design K. How to get K? Of course, by L1, L2, L3. Right? We did yesterday. I just skip this one. We get K 2.7. About 2.7. So this is gain adjustment. In order to get damping ratio 0.5, we need to use K 2.7. Is K equal to 2.7 to get damping ratio 0.5. And then I added some question, some more exact question here. Calculate the settling time, peak time, and steady state error when the system operates at damping ratio 0.5. Okay, we get the closed loop pole S equal to here is about minus 0.4 plus J 0.7. I took from here, I just put 0.4. It's 0.399 plus 0.696. Then we can calculate for settling time, 4 over zeta omega n. 4 over 0.4 is 10 seconds. And peak time, pi over 0.7. You can calculate, I do not have the value. And also we want to find error. Remember, error is mentioned here to RAM input. Is limit S to 0 SES. Is RAM input is 1 over limit S to 0 SES. SGS. Sorry, ini SES. Okay, please look into it back on error, formula for error. Before that, have you did you learn this in 3133? Static error constant. Anyone?
I'm not sure, doctor, but I can't recall this from 3133.
Okay, never mind. Because I taught this in for my section last semester. I'm not sure whether the other section learned about this or not. Okay, please revise letter error. You will find that this is equal to 1 over K. K is 2.7 over 1 the pole is at 1 and and 4. 1 and 4. That is actually 4 over 2.7. 4 over 2.7. This is the error. Okay, please revise error. That is very important. Okay, next. Design K. This is another question. Question A, question B, another question. Design K, as the system is required to operate with a settling time 16 seconds. Now, instead of damping ratio 0.5, we want to get another K, a new K, so that the system operates at 16 seconds. With settling time 16 seconds. We want TS 16 seconds. Okay. That means I want my zeta omega n is zeta omega n is equal to 4 over 60, which is 1 over 4, 0.5, 0.25. That means we want the closed loop pole S equal to minus 0.25 plus minus J. We need to decide plus minus J value. By using the root locus, I can locate this point in which this is 0.25 negative. See the pole here, 0.25. And if the real axis is 0.25, J here is 1.3. This is from the root locus. So this is the closed loop code to give PS 16 seconds. That is the real axis for the real axis is 0.25. So that the TS is 16 seconds. And then we can calculate K. We can calculate for K using the formula K equal to L1, L2, L3. And if you calculate, you get about 7.85. Please do this. Okay, later. If you calculate, you get 7.85. Any question here? I'm showing you gain adjustment. Okay. First, to obtain damping ratio, the other one to obtain settling time. We can also ask you to find K to obtain peak time. Okay. Peak time you can get the y-axis value, the imaginary axis value. Then, of course, based on the root locus, you can find the real axis value. Okay, so we use the formula, this formula. Any question?
Doctor, can you go to the previous slide?
This one?
Yes, sir. The for the T settling, where did you get the 0.4 value from?
Again, louder,
Uh,
please.
where did you get the 0.4 value for in the T settling when you did 4
You
divided
mean
by
here?
0?
This one? You mean here? You mean this one?
Yes, doctor. Thank you.
It's actually from here. I just make it 0.4. It's actually 0.399 plus J 0.6961. It's from here. Okay, Ahmad?
Yes, doctor.
I took from here. And this is, of course, obtained if in the exam will be obtained by using a graph paper. Okay, we did this last time. I mean, last week or also yesterday. This is actually I just round it up. 399 plus J 696. Okay. Any other question? Then let's move on. So now we want to discuss about second order approximation. we know there are many formulas to calculate transient response specification. We can calculate for settling time, we can calculate peak time, overshoot, rise time. But all these formula only for a pure second order system. The formula that we use is actually applicable only for a second order system, a pure second order system. Pure meaning here is two poles, second order, that means the denominator is, the highest order is 2, and the other one is no 0. Must be something like this. K over S plus A, S plus B. Okay, S squared 2 zeta omega n S omega n squared. Okay. This is a purely second order system. And the formula here is only applicable to this type of system. But the one that we will normally solve is a higher order system. It's not second order. It's sometimes third order, sometimes fourth order. Okay, we normally not give higher than 4. Okay, either 3 or 4 order, fourth order. So now, how can we approximate a higher order system to second order, to second order system, so that the formula that we use is valid, can be used. It actually can be approximated by using that formula. Okay, I will erase all this. Let's see, let's discuss when we have third order, when we have 3 poles, 2 complex poles and 1 pole on the imaginary, on the real axis. Pole here, these 2 poles this system can be approximated as a second order system if the distance here from here to here is 5 times. If the poles, if the third pole is 5 times farther than the 2 poles. Okay, if the distance is 5 times, if this is 1, minus 1 here, minus 5. If here, minus 2, minus 10. Minus 3, minus 15. Minus 0.5, here 2.5. If 5 times, if more than 5 times, we can say that the pole here can be ignored. The effect is not much on the other two poles. And in this case, these two poles is known as dominant pole. They are dominant. The other one is not dominant. Therefore, we can approximate the system as a second order system. Therefore, in order to obtain or to validate whether the system can be approximated or not, we need to find the other pole. We need to find the third pole so that we can know how is the distance between the dominant pole and the other pole. Okay. So the discussion after this is how can we obtain the third pole so that we can do the validation. I will again remove this. How can we find the third pole? The third pole can be obtained by solving or by using this formula. We use this formula, KGSHS equal to -1. This is the properties of root locus. We can use this formula. Okay, let see this. This system is a third order system. Now, as mentioned at C here, check whether the second order approximation is valid for both cases. For both cases, we want to check whether they are valid or not. Okay, so we need to find the third order, the third pole. There are 3 poles. We can see here, this is a third order system. That means there are 3 poles. When we do zeta line, we get pole here. This is the closed loop pole. To obtain damping ratio 0.5, closed loop pole. And as I mentioned, we normally, the complex pole will come in pair. So here another one, here another one. Must be plus minus. So K0 here, it increase going out, K0 here. And remember, we have another branch, K0 here. It go like this to this place. So when K increase until here is breakaway point, then increase again. At this point, K equal to 2.7. K here, K here is 2.7. We calculate L1, L2, L3, multiply, then we get 2.7. 2.7. Here also K 2.7. But remember, there is another pole here. When K 2.7. Because at one time, there must be 3 closed loop poles. But the system is a third order system. So what we want to do next is to locate where is the third order system, third order pole. Where is the third poles? We know 2 here, this 1, 2, and this is the 1, but we need to do a calculation to obtain the third pole. It can be obtained by solving this equation. We know K S plus 1 S plus 4 equal to minus 1. So K is minus S plus 1 S plus 4, or can get S. I open the bracket S to the power of 3, 5S squared, 4S plus 4 plus K equal to 0. This is the equation that we get. And with K 2.7, the one that we obtain here, we will solve the equation. S to the power of 3, 5S squared, 4S plus 2.7 equal to 0. And now I want you to use your calculator to obtain the poles, or to solve the equation. Solve S to the power of 3. I think your calculator can do it. Now find pole of this, or roots of this. I want 3. Where is it, Amar?
Sir, minus 4.2.
Minus 4.2. Where is the other 2? Where are the other 2?
Minus 0.3995.
3.995.
996.
996 plus
plus 0.695
695, and the other one
is the conjugate negative.
How you get this? Calculator?
Yes, doctor.
Okay, you use calculator, you get this. You can see these two, S1 and S2, is actually similar here. See, 3.99, 0.696, plus minus. And here, as mentioned, as you saw, you get S here is minus 4.2. This is the third closed loop pole. So we have here minus 3. Sorry, minus 0 point, right? 0.3. Minus 0.396 and minus 4.2. Next question. Can we approximate the system as a second order system? Yes or no? Can we approximate the system here as a second order system?
No,
No, why?
it's not 5 times larger, so it's not possible. 5 times larger would be minus
5
1
times
point.
meaning from
Minus
here.
1. Yes, it would be minus 1.98 if you multiply 0.396.
5 times meaning 4.2 over, in this case, 3.96. It's more than 5, right? That's what we mean by the distance between those poles. I will divide 4.2 by 0.39, which is, of course, more than 5. Therefore, the approximation is valid. Any question? I use also MATLAB. I also use MATLAB to check the validity of the second order system. This is the one that we just discussed. You see, 0.399, gain 2.7. The other one, when the same gain, 2.7, I could not get exactly here 2.7 to here 2.7. The pole is at minus 4.2. So the distance is 4.2 over 0.399 is more than 5. So it's valid. I also checked the other problem that we saw, which is to obtain settling time 16 seconds. So the pole here is 0.25 plus J 1.3. Of course, we have also conjugate negative J 1.3. The gain is 7.85. There is another pole here when at the same gain 7.85. The pole is minus 4.5. So in order to check whether it is valid or not, we divide 4.5 with 0.25. Of course, again, a lot more than 5. Also valid. So second order approximation is valid for both cases. Any question? This is another example. I just go through fast. We already know this one. This is another example. Now the pole is -2, -4, -6. I want to find K to yield 10% overshoot. Of course, we need to find zeta. This is the result. Zeta is 0.59 to get overshoot 10%. Okay. The pole here is this, the closed loop pole. Here, minus 2.03 J 2.77. Of course, we can get the settling time Ts over 4 over zeta omega n. We get 1.97. Peak time pi over omega d. We get 1.13. You can calculate error. And we can also calculate the third pole. Is these are the open loop poles, and of course we have another one here, third pole. Please apply the formula to get the third pole, which is, if you calculate, you get minus 7.95. So pole here, here, and here. 3 poles. Use the formula, calculate the pole, you get 7.95. So next question is the approximation value. Is the second order approximation value. Anyone can help? Is the approximation valid?
No.
We need to get the distance. 7.95 divided by 2.03 is surely less than 5. Therefore, not valid. Not valid meaning all these beside error, the other transient response specification that we calculated cannot be used. This is actually not correct because the approximation is not valid and the formula shouldn't be used. I will stop here. We will discuss more on a little bit. We will start to discuss controller, PI controller. We have done gain adjustment. Then we will start with PI controller in the next lecture.